All right, so this is section 6.1, first section in chapter 6. We're going to look at angles and their measure. We're going to go so far into angles, it's crazy. So we have a point. If I am going in any direction from a point, it's called a ray. So a ray has a starting point and a direction. A line we've been classically defining since before Algebra 1. It's a straight. It's got a line is indefinite. It goes on forever and ever and never stops. So an angle, and this little symbol here is called alpha. So angle alpha is where two rays meet, and it's the angle measure between the initial side of your ray, of your initial ray, and your terminal ray. So we have a vertex, an initial side, and a terminal side. We go counterclockwise is considered positive. So counterclockwise is positive, and we usually will rotate counterclockwise. If your angle is negative, that means you are going clockwise. And then this symbol here is beta. If you look at them, it looks kind of like an A for alpha. This kind of looks like a little B for beta. And then this is gamma. Looks like a Y. What else? So if we are going counterclockwise, we can go all the way around our circle, 360 degrees, and then that alpha measure, and end up at the same point, or end up at the same place as our initial angle. So this is the same two sets of rays that meet at a vertex, but three different angles that could describe how we get from the initial side to the terminal side. So if we start looking at it in Cartesian coordinates, our x and our y, we line up our initial side with our x-axis, and it's the positive version of our x-axis. And then we rotate counterclockwise, so our terminal side goes to the left, as long as we're under 360. And this is called standard position, and theta is positive, because if we're going counterclockwise, we're positive. Okay. So if we are in standard position and we are saying theta is negative, then it bumps us clockwise our theta angle. And this is, if theta is more than 90 degrees and less than 180, then theta lies in quadrant 2. If theta is between negative 90 and 0, then we're in quadrant 4. Or, I guess theta could be a quadrantial angle ends up on our axis. Okay, now we're going to start talking about moving and shaking. One revolution around the circle is 360 degrees. And as somebody who drove 15 hours yesterday, the wheels on a car go in a circle. And so anything that is usually circular motion related, we talk about in terms of revolutions. So right angle is 1/4 of a revolution. It's 90 degrees. It goes counterclockwise. We'll get this particular right angle. A straight angle is half of a revolution, or counterclockwise, 180 degrees. Okay, so now we are going to draw some angles. So I would do this definitely on graph paper. I'm drawing angles because having that X and the Y. So 45 degrees starts in standard position and goes up to the sky, 45 degrees. -90 starting in standard position rotates clockwise so that its terminal side is pointing down. 225. Well, 180 is at that straight angle, and then 100. So here's 180. So then we're going 45 degrees more. Sorry, it's 20. I'm not this slow. So it's straight angle and then 45 degrees more. And then last but not least, 405, anything over 360, you subtract out the 360 to see where that terminal side is going to be. So it goes all the way around back to the initial place and then up 45 degrees. All right, so now we're going to convert between decimals and degrees, minutes, seconds, and when we're talking about measures for angles. I love degrees, minutes, and seconds because it reminds me of, like, I'm a little bit of a ship captain. It's how people describe coordinates. So in a counterclockwise revolution of 360 degrees, every 1 degree is 60 seconds, and every 1 second is 60 minutes. So we use one mark here. So this little circle, we know the degrees, and then 1 mark is minutes, and 2 marks is seconds. So if we're going to convert 40 degrees, 12 minutes, 5 seconds to a decimal, remembering that 1 minute is 1/60th of a degree, and 1 second is 160 times 160. We use these as our conversion factors. So we know we have 40 degrees. That stays the same from our conversion from degrees, minutes, seconds to just a decimal. We have 12 minutes. So 12 minutes is 1/60th of a degree. So there's our conversion factor there. And then our conversion factor for seconds, so we have 5 seconds, is 1/60 times 1/60. So that's 40 plus 0.2 plus 0.0014. It does say round to the nearest 4 decimal places. So that is 40.2014. All right, so this case we are backwards. We have the degrees in decimal. We want it to be in degrees, minutes, seconds, and we're going to round to the nearest second. So the first thing we're going to do is we're going to split it up into its whole number and its decimal part. We want 0.562. This is in degrees. We want it in minutes. So our conversion from minute to degree is times 1 over 60. So if we are already in degree and we want to convert it to minutes, we're going to do the opposite, or multiply it by 60. So we multiply 0.562 by 60, and we get 33.72, and then we're going to take that 0.72, and it wants us to round to the nearest minute. So we're going to take, once again, take our decimal portion, multiply it by 60, because there are 60 seconds in every minute. And we get 43.2, but it says round to the nearest second, so that's going to be just 43. So it's 78 degrees, 33 minutes, 43 seconds. Okay, so we're going to talk, this is when you know you're a grown-up, when in math terms, when we can stop talking about degrees and start talking about radians. So 1 radian is another way to find the measure between the initial side and the terminal side. Okay, arc length of a circle. So the S part here is the arc length of the circle. This little sector has, this is the arc length of just this section of the circle. This little section has a degree of theta and a radius of r. The radius is going to be the same here as well, and the proportion between theta and theta 1 is going to be equal to S over S1. So that's how we can say the arc length is S is equal to the radius times theta, but please note, theta is in radians. So this is a formula for arc length in radians. It's different than the one we were using from geometry. Okay, so let's see how this works. Find the length of the arc of a circle of radius 4 meters, subtended by a central angle of 0.5 radians. So 4 times, you just multiply the radius times the theta, or the radians, and you get 2 meters. All right, so let's get our conversions from degrees to radians and radians to degrees. 1 revolution around the circle is 2 pi radians. And so halfway around the circle, or 180, is going to be pi radians. So 1 degree is pi over 180 radians. And 1 radian is 180 over pi degrees. So if we have 30 degrees, we're going to use our pi over 180 to get our radians. So 30 times pi over 180, 30 over 180 is 1/6. So we have 1/6 pi, or pi over 6. We do the same thing with 120. Multiply that by pi over 180, so you have to get really good at simplifying your fractions. That's 2 pi over 3 radians. Negative 60, same calculation, it's negative pi over 3 radians. 270 pi over 180 is 3 pi over 2. And last but not least, 104 pi over 180. When your fraction doesn't simplify down, you can write it as an approximate radian. Okay, now we can convert it back. When I have pi over 3 radian, I'm going to multiply that by 180 over pi. The pi's cancel out because degrees don't have pi in them. And pi over 3 is 60 degrees. Negative pi over 2, multiply that by 180 over pi, and you get negative 90. 5 pi over 6 times 180 over pi, you get 150. And then we can obviously have decimal degrees. So 5 radians is pi, or 180 over pi. That's approximately 86.48 degrees. All right, so this little chart here, I would definitely keep this handy somewhere because these are frequently used degrees and radians and their radian conversions. We're going to see these radians come up over and over again, and it's important for us to know where they come from. All right, finding the distance between two cities. This is fun. The latitude of a location L is the angle formed by a ray drawn from the center of the Earth to the equator and a ray from the center of the Earth to L. Glasgow, Montana is due north of Albuquerque. So here we're looking at specifics. New Mexico. Find the distance between Glasgow, 48 degrees, 9 minutes north latitude, and Albuquerque, 35 degrees, 5 minutes north latitude. Assume that the Earth's radius is 3,960 miles. Oh, awesome. Okay, so now we have to find the measure between these two cities. So we're going to subtract 48 degrees, 9 minutes from 35 degrees, 5 minutes. So we get 13 degrees, 4 minutes. That is this guy right here. And then we can use arc length. S equals r theta, and as long as theta is in radians, but we don't have radians, so we have to convert. So first thing we do is convert to a decimal. So this is 4 times 1 over 60, or 13.0667. Then we times it by pi over 180 to get our radians. So this is approximately 0.228 radians. So what we're trying to do is find the distance between Glasgow and Albuquerque. That's our arc length. We know that the angle between them is 0.228. We know that the radius of the Earth is 3,960. So we're going to take the 3,960 times it by the radians, and we get approximately 903 miles. All right, let's push on and find the area of a sector of a circle. So we know if we know theta and we know the radius, we can find the area of this shaded sector. Because the areas are proportional, we can say that the area of a sector is 1/2 r squared theta. What's the area of a sector? R has to be in, or sorry, theta has to be in radians. If theta is not in radians, this doesn't work. So let's see how to use that formula. Find the area of a circle of radius 5 feet formed by an angle of 60 degrees. So So we need that 60 degrees in radians in order to use the formula. So we go 60 times pi over 180 is pi over 3. Then we plug it into the formula. 1/2 radius squared, 5 squared, times radians is 25 pi over 6. We get the approximation because it's asking us to. 2 decimal places, it's about 13.09 feet. All right, now we're going to find a linear speed of an object traveling in a circular motion. This is how your car converts how fast your wheels are turning with how fast your car is actually moving. So the formula for linear speed is S over T. S is the arc length and T is time. So it's how fast you're moving through this arc length. Angular speed, so this is linear speed, so we're taking the arc length. So we are saying we're not talking linear speed, we're going to talk about angular speed. So how fast I'm moving through this angle theta in terms of time. So if we put this together, V is equal to R times theta. V equals R times theta. Sorry. R. So this is, this W is a lowercase omega. So V equals R omega. So let's apply that. A child is spinning a rock at an end of a 3-foot rope after he gets in trouble by his mom for spinning a rock around his head at a rate of 160 revolutions per minute. Find the linear speed of the rock when it's released. So his little rope is 3 feet long. We know he's got 160 revolutions per minute. We're going to convert that to radians. 2 pi radians is 1 revolution, so it's 320 pi radians per minute. The speed is R omega. We found that omega is 320 pi, so it's 3 times 320 pi. And we get 960 feet per minute. That thing's cooking. So we want to convert that to miles per hour. There are 5,280 feet in 1 mile. And then there's 60 minutes in 1 hour. So that's 960 times 60 divided by 5,280. That's approximately 10.9 miles per hour. That thing will put a dent in your forehead for sure.